Yeah, this number 15. I need to give you, so I need to give you a formula for this, this question. All right. For tower of Hanoi problem, okay, n disks, given n disks, then the number of moves equals 2 to the n minus 1. Okay. The number of moves you solve the Pascal's triangle using our recursive algorithm, you will get this number of moves, 2 to the n minus 1. Okay. For example, okay, we did n equals 3, right? We did n, so slow. We did n equals 3 case. Remember, we need 7 moves. Okay, we need 7 moves. Example, e.g., e dot g dot. E dot g dot, e.g. example. Okay, so 2 to the third minus 1 equals 7. The formula. Okay, why is that? Why is that actually here? I can show you a little bit. Actually, I plan to explain this in my PowerPoint slides. But so here, we can get a recurrence equation here. Remember, when we need to, so here, let's recall, how do we do the recurrence relation, that procedure? Let's recall that procedure, recurrence relation, okay? When we solve the P of n, we need to, so here, when we solve the P of n, we need to, the first step, we need to do P of n minus 1 first, okay? After that, we need to make one move. Remember the bottom disk, move that largest bottom disk to the destination pad, okay? After that, we need to do another P of n minus 1, okay? All right. Based on this recurrence relation, let's consider the number of moves. Let's count the number of moves for n disk, C of n function. C of n function, in order to get a C of n function, counting this many moves, we need to do n minus 1 disk problem twice. That means 2 times C of n minus 1. Okay. It's too slow here today. C times 2 times C of n minus 1 plus a constant number 1. One move. Bottom disk, one move. Okay? That means we need to solve this recurrence relation. Solving this recurrence relation. Okay? Here, let me show you how to solve. There is a smart trick we can apply to solve this recurrence relation. Do subtraction both sides by 1. By, let me see. Oh, not subtraction. addition. Do addition both sides by 1. Why? You may ask me why. Yeah. So because we got, so our goal, why we do this transformation, we want to make both sides have the similar structure. Equation, both sides, we want them have similar structure. So by adding 1 both sides, left-hand side will be C of n plus 1. Right-hand side will be 2 times C of n minus 1 plus 2, right? Plus 2, we can factor that 2 common factor out. C of n minus 1 plus 1. Okay? Why we do this? Why we do this transformation? The reason is simple. The reason is we want to make the left-hand side structure C function plus 1. Right-hand side inside the brackets, the structure, they have similar structure. How about that? Similarity. We explore the similarity structure both sides. Okay? Yeah. Because this kind of structure similar, can we use a new function d of n to replace this C of n function? Yeah. Yeah. D function equals 2 times d of n minus 1 function. How about that? We use that C of n plus 1. We do substitution. This whole thing, we use a new function, d function, d of 1 to replace it. The reason is this d version looks simpler than C version, right? Constant is gone. All the constant numbers all gone. Okay? We only d of n equals 2 times d of n minus 1. Okay? Yeah. Can we apply this recurrence relation another time? 2 squared times d of n minus 2. And so on. Can we keep doing this again and again? Keep doing this again and again. Okay? Dot, dot, dot. Until we get a power, kth power, 2 to the k times d of n minus what? 2 to the k, if we do this recurrence relation multiple times, 2 to the k times d of n minus k. Yep, because 2 to the first, d n minus 1. 2 squared d n minus 2. 2 to the k d n minus k. How about that? Okay, yeah. Then when we move to the last one, 2 to the n minus 1. How about that? 2 to the n minus 1 d of 1. How about that? D of 1. N minus 1 plus 1 invariant n. Here we use the invariant n. Invariant idea. N minus 1 plus 1 equals n. N is our invariant. We use invariant n to keep track of all the terms, all the steps. Okay, keep track of all the steps. K plus n minus k, that's n invariant. N invariant. Okay, yeah, here. So the last one, 2 to the n minus 1 times d of 1. What is d of 1? D of 1. Yeah, because d of 1 equals C of 1 plus 1, right? What is C of 1? One disk, how many moves you make for one disk? One move, right? 1 to the destination, 1 move. So C of 1 is 1, 1 plus 1 is 2. That means D of 1 equals 2. Okay? 2 times 2 to the n minus 1, you get a 2 to the nth power. So the D function equals 2 to the n. How about C function? C function just the D function minus 1. Okay. C of m equals 2 to the n minus 1. Okay. Yeah. So that's the formula I gave you before. Here, I show you how to find the answer. We do n minus 1 twice. Yes, 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 yeah, yeah. Just recall. Also recall our pseudocode. We do recurrence call twice, right? At the beginning once, then we make a middle move. Then after that we move to another time. N minus 1 twice. Yeah. So we have that too. Coefficient 2. Okay. Yeah. So that reason. Now, think about for this question, if you can apply this formula directly, now you can apply 2 to the n minus 1. Yeah. So m1 disk 2 to the m1 minus 1, that's the number of moves, right? m2, 2 to the m2 minus 1, that's the number of moves. You can use that formula, right? Yes, and try to figure out what is little m1, little m2. With this formula, try to figure out. Little m1, little m2. Oh, you solve the problem after you go home. Yeah, you're not here, not solving here. Yeah, think about. Yeah, I just ask you to think about. Connect. After you get this formula, it should not be that hard. Okay. Yeah.